Significance testing of patterns in data visualizations. Suppose you visualize your data and you observe a pattern. For example, a cluster in a scatter plot or a high value in a time series. Is this pattern real, or is it just a random artifact of the data? This kind of problem is solved with statistical significance testing. If a pattern is extreme compared to our assumptions, then it is not random. In significance testing, we use a test statistic t and its distribution under the null hypothesis. For us, the visual pattern corresponds to the test statistic, and the null distribution encodes our assumptions about the data. Combining visual exploration with significance testing is not straightforward. Normally in significance testing, you first formulate a hypothesis, and then you look at the data. In contrast, in visual exploration, you might first look at the data and then formulate hypotheses. A naive solution for this would be to formulate all possible hypotheses and then look at the data. However, in a visual exploration, the number of possible hypotheses is very large. If we apply multiple hypothesis correction to reduce the inevitable false positives, then we lose all statistical power and find no significant patterns. We improve statistical power by leveraging the analyst's knowledge. If you have prior knowledge about the data, either from expertise or experience, then you formulate specific and focused hypotheses. This results in a smaller hypothesis space and improved power. A further improvement comes from the choice of multiple hypothesis correction. We use a min-p resampling procedure that takes into account the correlation structure of the data. This makes it less conservative than traditional methods like Porpheroni. We can omit the multiple hypothesis correction if our data is splittable. In the scatterplot example, we can split the data into two. One part is used for visual exploration, and the other part is hidden from the user and is used for testing observed patterns. The test statistic in this case is the number of points inside the marked region, and for the null distribution, we sample from datasets with the same marginal distributions by permuting the data. In the time series case, we cannot split the data, so instead we test multiple predefined test statistics simultaneously and then correct for multiple hypotheses using the min-p procedure. The test statistic is the value of the time series at each point, and for the null distribution, we sample Gaussian process priors. Our paper proposes a principled framework for testing the significance of visual patterns during visual exploration. This enables the user to determine whether observed patterns are real or just random artifacts of the data.